A spacecraft designed to study a metal asteroid millions of miles away turned its cameras toward an interstellar comet for 8 hours, and what it captured surprised scientists. This isn't how space missions typically work. You don't often get to use a billion-dollar spacecraft to observe something that wasn't part of the original plan, but NASA did exactly that, and what emerged from those 8 hours changed how we understand this visitor from beyond our solar system. Think about that for a moment. An interstellar comet, something that originated in another star system, travelled for who knows how many thousands or millions of years through the void between stars, and when it finally crossed through our neighbourhood, a spacecraft that was never designed to study comets happened to be in the perfect position to watch it. Not just watch it casually, but track it methodically, continuously for 8 straight hours, and during that window something unexpected revealed itself in the data. Stay with me here, because in the next several minutes, we're going to uncover exactly what NASA's Psyche spacecraft discovered during that tracking session, why it matters more than you might think, and what this tells us about visitors from other star systems. This isn't just another space story. This is about what happens when human ingenuity meets cosmic opportunity, and the results surprise even the experts. You need to understand something fundamental about space exploration before we go further. When NASA designs a mission, every single component, every instrument, every line of code, every operational plan is crafted with surgical precision for one specific purpose. The Psyche spacecraft wasn't built to study comets. It was built to journey to a metal-rich asteroid between Mars and Jupiter, a world that might be the exposed core of an early planet, and to unlock secrets about planetary formation that we can't learn anywhere else. Its cameras, its sensors, its entire operational framework, all optimized for one target, one goal, one destination years away. So when NASA announced that Psyche would be tracking an interstellar comet for 8 hours, it raised immediate questions. Why would they divert attention from the primary mission? What could this spacecraft possibly contribute to our understanding of a comet when it's designed for something entirely different? And more importantly, what unique perspective could Psyche add alongside the dozens of other telescopes and spacecraft observing this comet? The answer to that last question is where this story gets genuinely fascinating. Because what Psyche found during those 8 hours wasn't just useful data, it was unexpected data. The kind of information that makes scientists pause, recalibrate their models, and realize that this interstellar visitor is revealing characteristics nobody predicted. And you're about to learn exactly what those characteristics are. But before we get to the discovery itself, you need to appreciate the context. Interstellar objects don't come through our solar system often. In fact, before recent years, we had never confirmed one. We theorized they existed. Logic demands it, given that star systems eject material all the time, but actually detecting one, tracking it, and studying it before it disappears back into interstellar space? That's extraordinarily rare. When it happens, the entire astronomical community mobilizes. Every available telescope, every spacecraft with a camera, every observatory that can contribute does so, because the opportunity won't come again. That object is passing through once, and once it's gone forever. 3I Atlas. Our third confirmed interstellar visitor entered our solar system from beyond, moving on a trajectory that confirmed its extrasolar origin immediately. Not a long-period comet from our own Oort cloud, not an asteroid that got nudged into an unusual orbit. This was definitely from somewhere else, another star system, another stellar neighbourhood, a messenger from a region of space we may never physically visit in our lifetimes. When something like that appears, NASA doesn't hesitate. Resources get allocated, missions get adjusted, and spacecraft like Psyche, even though they're on their way to completely different destinations, get called into service for what amounts to cosmic reconnaissance. Because here's what most people don't realize. A spacecraft in deep space, even one designed for a specific target, carries instruments that can be astonishingly versatile when properly utilized. And Psyche's multispectral imager, the camera system designed to analyze the composition and characteristics of a metal asteroid, turned out to be perfectly capable of capturing critical data about a comet's behavior millions of miles away. So NASA made the call. For 8 hours on September 8th and 9th, Psyche would become a comet observer. It would track this interstellar visitor as it moved through our solar system, capturing images and data at intervals carefully calculated to maximize scientific return. 4 observation windows, 8 hours of tracking, 1 spacecraft, 1 comet, and a team of scientists waiting to see what would emerge from the data once it traveled back across millions of miles of space to reach Earth. What they found was not what they expected. And that's the part of this story that should capture your attention completely, because unexpected in science isn't a casual term. Scientists build models, make predictions, and design observations specifically to test hypotheses. When results come back unexpected, it means nature just taught us something we didn't know, challenged an assumption we were making, or revealed a characteristic that our models failed to predict. It means discovery in its purest form. During those 8 hours, as Psyche's cameras captured reflected sunlight bouncing off this ancient visitor from beyond our solar system, something about the comet's behaviour, its appearance, its characteristics emerged in the data that didn't match expectations. And understanding what that was requires understanding not just what Psyche saw, but why Psyche was uniquely positioned to see it in the first place. This is where the story shifts from interesting to genuinely important. Because what NASA discovered during that 8-hour window isn't just a footnote in the history of this particular comet's passage through our solar system. It's a data point that contributes to our broader understanding of how interstellar objects behave, what they're made of, where they come from, and what they can teach us about star systems beyond our own. Every observation matters, every hour of tracking contributes, and those 8 hours that Psyche dedicated to this task, they added a unique perspective that complemented what others were seeing. So here's what I want you to think about as we move forward. Somewhere out there, right now, this interstellar comet is continuing its journey. It came from beyond, passed through our solar system, got observed by some of humanity's most sophisticated instruments, and is now heading back out into interstellar space, where it will travel for eons before potentially encountering another star system. For a brief window, we shared space with it. We pointed our cameras at it, we studied it, and it taught us something. That 8-hour tracking session captured by Psyche is now part of the permanent scientific record, a contribution to human knowledge that will be referenced, analysed, and built upon for decades. But what exactly did it reveal? What was unexpected? What did Psyche see that prompted NASA to describe the findings in terms that suggest genuine surprise? That's what we're about to explore together, and I promise you the answer is worth your time. Hit that like button and drop a comment telling me what you think NASA found during those 8 hours. Are you tracking this story from home, on your commute, or somewhere under the same sky this comet is crossing? Let me know where you're watching from, because this discovery connects all of us to something that came from beyond our solar system, something ancient and mysterious that briefly passed through our neighbourhood and left us with knowledge we didn't have before. Now let me take you inside what makes the Psyche spacecraft uniquely capable of contributing to this observation, because understanding the tool helps you appreciate the discovery, and the discovery is where this story truly begins to reveal its depth. To understand why Psyche's 8-hour tracking session matters, you first need to understand what Psyche is and why it exists at all. This isn't a general-purpose observatory. This isn't a spacecraft designed to hop from target to target like some cosmic tourist. Psyche has one primary job, one destination that justifies its entire existence, and that destination is an asteroid unlike any other object we've ever studied up close. Out in the asteroid belt between Mars and Jupiter, there's a world that might not be a world in the traditional sense at all. It might be the exposed metallic core of what was once a much larger planetary body, a protoplanet that formed during the chaotic early days of our solar system, and then got smashed apart in a collision so violent that everything except the iron-nickel core got stripped away. What remains is essentially a metal world, a chunk of planetary innards that would normally be buried thousands of miles beneath a planet's surface, now exposed and waiting to be studied. That's where Psyche is going. That's what it was built to explore. The spacecraft launched with instruments specifically designed for that mission. A multispectral imager to map the asteroid's surface and determine its composition. A magnetometer to detect any residual magnetic field that might confirm this object's origin as a planetary core. A gamma ray and neutron spectrometer to analyse what elements are present. Every piece of hardware chosen for one purpose: understanding a metal-rich asteroid that could rewrite our understanding of planetary formation. So when NASA decided to redirect Psyche's attention toward an interstellar comet, it wasn't a casual decision. Spacecraft operations are expensive, both in terms of money and resources. Every maneuver costs fuel. Every observation sequence requires engineering time, planning, coordination, and data transmission bandwidth. You don't just point a spacecraft at something on a whim, especially not a spacecraft in the middle of a multi-year journey to a destination that's still years away. There has to be a compelling reason. There has to be value that justifies the diversion. The value here was twofold. First, interstellar objects are so rare and so scientifically important that when one appears, every asset gets mobilized. Second, and this is the crucial part, Psyche happened to be in a position where its observations could contribute something unique, Not redundant data that other telescopes were already capturing, but a genuinely different perspective, a different angle, a different set of measurements that would complement what everyone else was seeing. This is where the multispectral imager becomes important. This camera system doesn't just take pictures in the way you might think of a camera working. It captures images across multiple wavelengths of light, from visible spectrum into near-infrared, allowing scientists to analyze reflected sunlight and determine what a surface is made of, how it's structured, what materials are present. When you point that kind of instrument at a comet, you're not just seeing a fuzzy blob in space. You're analyzing the composition of the material surrounding it, the gases and dust that make up its atmosphere, the way sunlight interacts with those materials. NASA knew that this capability, combined with Psyche's specific location in space at the time the interstellar comet was passing through, would provide data that Earth-based telescopes and other spacecraft might not capture as effectively. The angle matters, the distance matters, the specific wavelengths being observed matter, and Psyche, despite being designed for an entirely different target, had the tools and the position to contribute meaningfully. So the decision was made. Psyche would track the comet. Mission planners worked out the observation sequence. Engineers calculated the pointing angles, the timing, the data collection parameters. Scientists prepared to receive and analyze whatever came back. And on September 8th, the tracking began. What's remarkable here isn't just that NASA chose to do this. It's that modern spacecraft are sophisticated enough, and mission operations are flexible enough, that this kind of opportunistic science is even possible. Decades ago, a spacecraft launched toward one target stayed focused on that target exclusively. The technology didn't allow for much deviation, and the operational mindset was rigidly fixed on the primary mission. But today, spacecraft like Psyche carry instruments with broader capabilities, and mission teams have the expertise and flexibility to seize opportunities when they arise. This interstellar comet represented exactly that kind of opportunity. A once-in-a-lifetime chance to study something from beyond our solar system, using tools that, while not specifically designed for comets, could absolutely provide valuable data if used creatively. And creativity in space science often yields the most interesting results, because you're pushing instruments to do things their designers might not have explicitly planned for, and sometimes, in those moments, you discover capabilities and insights that wouldn't have emerged otherwise. Psyche's cameras, built to handle the challenge of imaging a metal surface under harsh solar illumination, millions of miles from Earth, turned out to be more than capable of capturing the faint, delicate features of a comet's outer atmosphere as it reflected sunlight while moving through our solar system. The sensitivity was there, the resolution was there, the wavelength coverage was there, all the pieces aligned. But alignment of capability doesn't guarantee discovery. You still need the object you're observing to reveal something worth discovering. You need nature to cooperate, to present characteristics that your instruments can detect and that your analysis can interpret. And this is where the story takes its turn toward the unexpected, because what Psyche observed during those 8 hours wasn't just confirmation of what scientists already suspected. It was revelation of details that challenged assumptions and added unexpected complexity to the picture. The spacecraft captured 4 separate observation sequences over that 8-hour window. 4 moments when Psyche's cameras focused on this visitor from another star system, recorded reflected sunlight, measured wavelengths, and transmitted data back home. 4 snapshots, essentially, but snapshots taken with instruments sophisticated enough to extract extraordinary amounts of information from each exposure. And when scientists began analyzing that data, when they started comparing what Psyche saw with what other observatories were reporting, when they built models and ran calculations and cross-reference measurements, patterns emerged. Details became clear, and those details told a story about this comet that wasn't fully anticipated. This is the pivot point in our narrative, the moment where we transition from understanding why Psyche was observing to understanding what Psyche actually found. Because the spacecraft's unique capabilities and its fortuitous position in space would have been interesting on their own, but ultimately forgettable if the observations had simply confirmed existing expectations. What makes this story worth telling is that the data revealed something more, something that expanded our understanding, something unexpected. Before we dive into that discovery, though, there's one more piece of context you need. Those 8 hours weren't arbitrary. The observation window was carefully calculated based on when the comet would be at optimal distance and angle relative to Psyche, when lighting conditions would be favourable, when the spacecraft's other operational requirements could be temporarily set aside to focus on this secondary target. NASA doesn't waste spacecraft time. Every observation window represents a carefully balanced decision about what science is worth pursuing at any given moment. The fact that 8 hours got allocated to tracking an interstellar comet tells you how seriously NASA takes these opportunities. 8 hours of a spacecraft's operational time, millions of miles from Earth, dedicated to something that wasn't part of the original mission plan. That's commitment. That's recognition of the extraordinary nature of what was passing through our solar system. And that commitment paid off, because what emerged from those 8 hours of tracking, from those 4 carefully timed observation sequences, from the data that travelled millions of miles back to Earth to be analysed by some of the world's leading experts in cometary science, that data carried revelations that justified every second Psyche spent watching this ancient traveller from beyond. September 8th. Early in the month, when autumn was just beginning to hint at its arrival in the Northern Hemisphere, and when a spacecraft millions of miles from Earth began a task that would contribute valuable data to studying one of the year's most exciting astronomical visitors. For 8 hours spanning September 8th and 9th, Psyche locked its multispectral imager onto an interstellar visitor and began methodically capturing data. Think about what 8 hours means in the context of space observation. On Earth, 8 hours might feel routine, a workday, a long drive, a full night's sleep. But for a spacecraft tracking an object across the vast distances of the solar system, 8 hours represents a significant commitment of resources and attention. The comet was moving, Psyche was moving, Earth was moving. Everything in space is always in motion, and coordinating an observation that spans 8 hours requires precise calculations about where everything will be at every moment during that window. NASA's mission planners calculated the geometry down to the finest detail. They knew where Psyche would be in its trajectory toward the asteroid belt. They knew where the interstellar comet would be in its path through our solar system. They knew the angles, the distances, the lighting conditions, and they designed an observation sequence that would capture 4 separate datasets during that 8-hour window. 4 moments when Psyche's cameras would record what the comet looked like from that specific vantage point in space. 4 observations, 4 opportunities to capture reflected sunlight bouncing off the comet and its surrounding material. 4 data points that would eventually be transmitted back to Earth, analysed, compared, and integrated into the broader scientific understanding of this visitor from beyond. The distance between Psyche and the comet during this tracking session was substantial. We're not talking about a close flyby. We're not talking about the spacecraft passing within a few hundred miles of the comet, like some missions do with their targets. Psyche was millions of miles away from the comet when it conducted these observations. But distance, while it limits some kinds of measurements, doesn't necessarily prevent meaningful science when you have the right instruments and the right conditions. Psyche's multispectral imager, even across millions of miles of space, could detect and analyse the light being reflected off the comet, could measure wavelengths, could extract information about composition and structure and behaviour. Distance compresses the view, makes the object appear smaller, reduces the spatial resolution you can achieve, but it doesn't eliminate the fundamental capability to gather scientifically valuable data. And that's exactly what happened during those 8 hours. Data accumulated, observations recorded. Photons that had bounced off an object from another star system travelled across millions of miles of space to be captured by sensors on a human-made spacecraft, converted into digital information, and transmitted back to Earth for analysis. When you think about that process, about how each step in that chain represents decades of technological development and scientific expertise, it's genuinely remarkable that we can do this at all. But we can do it. And during those 8 hours we did it with precision and purpose. Psyche watched, the comet moved, light reflected, data accumulated, and slowly a picture began to form of what this interstellar visitor actually looked like from a perspective nobody else had. The timing of this observation window was significant for another reason. This wasn't the comet's closest approach to the Sun. This wasn't the moment of maximum activity or brightness. This was a carefully chosen window when Psyche's position relative to the comet would provide a useful viewing angle, when the spacecraft could dedicate time to the observation without compromising its primary mission timeline, and when the data captured would complement what other observatories were seeing from their vantage points. In space science, there's enormous value in having multiple observers looking at the same object from different locations. Each observer sees something slightly different. Each perspective adds information. Each dataset fills in gaps that other observations might miss. Earth-based telescopes see the comet from Earth's perspective, obviously. Hubble sees it from low Earth orbit. Other spacecraft see it from their positions in space. And Psyche, from its location millions of miles away on its journey toward the asteroid belt, added yet another piece to the puzzle. What's fascinating about this multi-observer approach is how it builds a three-dimensional understanding of an object that any single observer would see only in two dimensions. By combining observations from multiple angles, scientists can reconstruct the comet's true structure, behavior, and characteristics in ways that would be impossible from a single viewpoint. It's like the difference between seeing a photograph of a sculpture and walking around that sculpture to examine it from every side. Both provide information, but the latter gives you a complete understanding. Psyche's 8-hour tracking session was contributing to that complete understanding. It was adding the perspective from millions of miles away, from an angle that Earth-based telescopes couldn't achieve, at a distance that provided its own unique set of advantages and challenges. And as the hours passed, as each observation sequence completed and the data began its journey back to Earth, scientists waited with the kind of anticipation that comes from knowing you're about to learn something new. Because here's the thing about observing interstellar objects. We don't have much baseline knowledge. When you study a comet from our own solar system, you can compare it to dozens or hundreds of other comets we've observed before. You know what typical comets look like, how they behave, what characteristics are common and which are unusual. But with interstellar visitors, every observation is essentially a first. We're building the baseline in real time. We don't know what typical looks like for objects from other star systems because we've only confirmed a handful of them, and each one has shown unique characteristics. So when Psyche's data started arriving, when scientists began the careful process of analysis and interpretation, there was no firm template for what they should expect to see. There were models, certainly. Theories about how comets from other star systems might differ from our local comets. Predictions about composition and behavior based on what we know about stellar environments and planetary formation in general. But theories and predictions are just educated guesses until data confirms or challenges them. The data from Psyche's 8-hour tracking session did both. It confirmed some expectations, and it challenged others, and it's the challenging part, the unexpected elements, that make this story worth examining in detail. During those 8 hours, Psyche captured images and spectral data that revealed specific characteristics of the comet's behavior. Not just it's moving, or it's reflecting light, but detailed information about the material surrounding the comet, the way that material was interacting with sunlight, the composition and structure of what scientists call the coma, the cloud of gas and dust that surrounds a comet's solid nucleus. Every comet has a coma when it gets close enough to the sun for solar heat to vaporize some of its ice. Material sublimates off the surface, carrying dust with it, creating this atmosphere that can extend for thousands or even millions of miles around the tiny solid core. The coma is where much of the comet's visible activity happens, and studying it tells you enormous amounts about what the comet is made of, how active it is, and what processes are driving that activity. Psyche's multispectral imager was perfectly suited to studying a coma. The instrument could detect the reflected sunlight coming from the dust particles in the coma, could analyze different wavelengths to determine what gases were present, could measure the overall brightness and extent of this surrounding material, and during those 8 hours it did exactly that, building a detailed portrait of this interstellar comet's atmospheric envelope. What it found was a coma that behaved in ways that weren't entirely predicted, not wildly different from expectations, but different enough that when scientists reviewed the data, they noted characteristics that deserved further investigation, that suggested this comet wasn't a perfect match for the models they'd been using, that indicated there was more complexity here than initial observations had suggested. This is where the word unexpected enters the conversation, because the data showed a coma that was fainter than some predictions suggested it should be. A coma with characteristics that implied specific things about the composition of the nucleus and the processes happening on its surface. A coma that, when combined with data from other observers, painted a picture of an interstellar visitor that was distinctly its own entity, not simply a carbon copy of comets from our own solar system wearing a different origin label. That faintness, that specific set of characteristics captured during Psyche's 8-hour observation window, became a key piece of the larger puzzle scientists were assembling about this visitor from beyond, and understanding what that faintness means, why it matters, and what it tells us about where this comet came from requires diving deeper into the details of what Psyche actually saw and how that data got interpreted. But before we go there, take a moment to appreciate the journey this information took. Photons reflected off a comet that originated in another star system. Those photons travelled millions of miles through space. They hit sensors on a spacecraft built by human hands and launched from Earth years ago. That spacecraft converted those photons into data, then transmitted that data as radio signals across millions of miles of empty space back to Earth. Antennas here captured those signals, computers decoded them, and scientists interpreted them. The chain from ancient comet to human understanding spans distances and timescales that should humble us, but instead it demonstrates something remarkable about what our species has learned to do. We've learned to reach across the void and touch, at least intellectually, objects from other star systems. We've learned to turn light into knowledge. And during 8 hours in early September, on a spacecraft named after a metal asteroid it won't reach for years, we did exactly that with an interstellar visitor that briefly passed through our cosmic neighbourhood. Now, let me show you what that knowledge actually revealed, because the discovery itself is where this story finds its true significance. Here's the first piece of the unexpected discovery, and it might not sound dramatic at first. But stay with me, because the implications ripple outward in ways that matter deeply. Psyche's 8-hour tracking session allowed astronomers to refine the trajectory calculations for this interstellar comet with a level of precision that wasn't achievable before those observations. On the surface, that might seem technical, even mundane. Trajectory refinement. It sounds like bureaucratic space jargon, something engineers worry about, but that doesn't touch the realm of genuine discovery. But you need to understand what trajectory refinement actually means in the context of interstellar objects, because once you do, you'll realize why this matters. When an object enters our solar system from interstellar space, tracking its exact path is extraordinarily difficult. We're not talking about satellites in Earth orbit that we can monitor constantly with ground-based radar. We're not even talking about asteroids from our own solar system that we've been cataloguing for decades and whose orbits we can predict with extreme accuracy. We're talking about something that came from outside, moving at speeds determined by wherever it originated, following a trajectory shaped by gravitational interactions we can never fully reconstruct, and passing through our solar system on a path we only get to observe for a limited time before it disappears back into interstellar space forever. Every data point we can gather about that trajectory is precious. Every observation that helps us understand exactly where it's been and where it's going adds to our ability to model its path, to predict where it will be at any given time, and most importantly, to understand the forces acting on it. Because interstellar objects don't just move in straight lines. They're affected by the sun's gravity. They're affected by the gravity of planets they pass near. If they're comets, they're affected by outgassing. Material ejecting from their surface creates tiny thrust forces that can alter their trajectory in ways that pure gravitational calculations wouldn't predict. All of these factors make tracking interstellar objects a complex challenge that requires observations from multiple locations over extended periods. You need baseline measurements from early in the object's passage through our solar system. You need follow-up observations as it continues its journey. You need data from different angles, different distances, or different times. And every additional observation helps constrain the possibilities, helps narrow down the exact path, helps improve the precision of your trajectory model. This is where Psyche's contribution becomes significant. The 8 hours of tracking, those 4 observation sequences captured from millions of miles away, provided data points from a perspective and distance that complemented what Earth-based telescopes and other spacecraft were seeing. That unique vantage point meant Psyche could measure the comet's position at specific times with its own precision, and when those measurements got integrated into the broader trajectory analysis that NASA and other space agencies were conducting, the result was an improvement in our certainty about where this object has been and where it's going. Why does that certainty matter? Because when you're dealing with objects that pass through our solar system, even objects that pose no threat to Earth, understanding their trajectories teaches you something fundamental about the dynamics of our cosmic neighbourhood. It tells you how objects move through the gravitational landscape of the Sun and planets. It tells you how non-gravitational forces like comet outgassing affect orbital paths, and in some cases, for some objects, it tells you whether you need to pay closer attention as time goes on. Now, let me be absolutely clear about something before we go further, because I don't want to create alarm where none exists. This interstellar comet poses zero threat to Earth. NASA confirmed that explicitly. The trajectory calculations, including the refinements made possible by Psyche's observations, show conclusively that this object is passing through our solar system at a safe distance and will continue on its way without coming anywhere near our planet. That's not what the trajectory refinement was about. It wasn't about planetary defense in the immediate sense, though. The techniques and expertise developed for tracking interstellar objects absolutely feed into our broader planetary defense capabilities. The refinement was about scientific understanding. It was about knowing, with maximum precision, exactly what path this visitor from another star system is taking through our neighbourhood. And that precision revealed something interesting about the comet's behaviour that wouldn't have been clear without the additional data Psyche provided. When scientists first detected this interstellar visitor and began calculating its trajectory, they were working with limited observations and had to make certain assumptions. As more data accumulated from various telescopes and spacecraft, those initial calculations got refined. But even with multiple observers, there were still uncertainties, still margins of error, still questions about exactly how the comet was moving. The trajectory fit the models within acceptable ranges, but those ranges were wider than scientists would have preferred. Psyche's observations helped narrow those ranges. The data added precision to position measurements at specific times, and with that precision came the ability to model the comet's path with greater confidence, to reduce the uncertainty in predictions about where it would be at future dates, and to better understand the forces acting on it as it travelled. What emerged from that refined trajectory analysis was confirmation that this comet is following a path consistent with its interstellar origin, moving at speeds that tell a story about where it might have come from and how long it's been travelling. The trajectory showed influences from the Sun's gravity, as expected, bending the comet's path as it passed through the inner solar system. But it also showed subtle indications of non-gravitational effects, the kind of slight trajectory modifications that happen when a comet is actively outgassing, when material ejecting from its surface creates tiny thrust forces that push against the comet's motion. Those non-gravitational effects are actually scientifically fascinating, because they tell you something about the comet's activity level. A completely dormant object, one that's just a frozen chunk with no active outgassing, moves purely under gravitational forces, but a comet that's actively sublimating ice as it gets heated by the sun. The comet experiences additional forces, and those forces show up in trajectory analysis as small deviations from purely gravitational motion. Psyche's observations contributed to detecting and quantifying those deviations. The refined trajectory showed that this interstellar comet was indeed active, was indeed outgassing, and was indeed experiencing the subtle trajectory modifications that come with that activity. That confirmation might seem obvious. It's a comet, of course it's outgassing. But remember, we're dealing with an object from another star system. We don't know for certain that interstellar comets behave the same way as comets from our own solar system. Every confirmation, every measurement, every data point that shows us what these visitors actually do when they pass through our neighbourhood adds to the foundation of knowledge we're building about how planetary systems in general work. The trajectory refinement also allowed NASA to better coordinate observations with other spacecraft and telescopes. When you know exactly where an object is going to be at any given time, you can plan observation windows more effectively. You can tell Hubble when to point its cameras. You can tell ground-based telescopes when the object will be at optimal viewing angles. You can coordinate the entire observational campaign with precision that maximizes scientific return from every available instrument. That coordination, that ability to say with confidence, the comet will be here at this time, and that's when you should observe it, stems directly from trajectory work that includes contributions like Psyche's 8-hour tracking session. Every spacecraft that contributed data, every telescope that captured position measurements, every observation that helped refine the orbital calculations played a role in enabling the broader scientific campaign that studied this interstellar visitor during its passage through our solar system. And here's where the story takes another turn, because trajectory refinement was just the first layer of what Psyche's observations revealed. The second layer, the part that truly earned the descriptor unexpected, had to do with what Psyche saw when it looked not just at where the comet was, but at what the comet looked like, at the characteristics of that faint cloud of material surrounding the nucleus, at the coma itself, and what that coma revealed about this ancient traveller's composition and behaviour. Trajectory told scientists where the comet had been and where it was going, but the coma data, the spectral information captured by Psyche's multispectral imager during those 8 hours of observation, told scientists something deeper about what this object actually is, what it's made of, and how it differs from or resembles the comets we're familiar with from our own solar system. That's where the truly unexpected findings emerged, in the details of what Psyche observed about the comet's atmosphere, about the way sunlight was interacting with the material surrounding the nucleus, about the composition and behaviour of gases and dust that had travelled for countless ages across interstellar space, and were now, for a brief window, revealing their nature to human instruments. This is the transition point where our story moves from the technical achievement of refining a trajectory to the scientific revelation of discovering unexpected characteristics in the comet itself, characteristics that Psyche was uniquely positioned to observe and that added crucial pieces to our understanding of what interstellar objects can teach us about the universe beyond our solar system. Now we arrive at the heart of the unexpected discovery, the aspect of Psyche's observations that truly surprised scientists and added something genuinely new to our understanding of this interstellar visitor. During those 8 hours of tracking, as Psyche's multispectral imager captured reflected sunlight from the comet, the data revealed characteristics of the coma that weren't entirely what predictions suggested they should be. And to understand why this matters, you first need to understand what a coma actually is and what it tells us about a comet. Imagine a comet's nucleus, the solid core, as a dirty snowball in space. It's a mixture of ice and rock, dust and frozen gases, material that's been preserved in deep freeze for billions of years. When that nucleus is far from the sun, out in the cold outer reaches of a solar system or drifting through interstellar space, it's essentially dormant. Nothing happens. It's just a frozen chunk moving through the void. But as it gets closer to a star, as solar radiation begins heating its surface, something remarkable occurs. The ice starts to sublimate, turning directly from solid to gas without melting first, and as that happens, the gas carries dust particles with it, ejecting material off the surface and into space. That ejected material doesn't just disappear, it forms a cloud around the nucleus, an atmosphere that can extend for enormous distances, sometimes millions of miles in the most active comets. This cloud, this extended atmosphere of gas and dust, is what astronomers call the coma. And the coma is extraordinarily revealing because its properties tell you almost everything worth knowing about what's happening on the comet's surface and what the nucleus is made of. When you study a coma, you're essentially sampling the material that makes up the comet itself. The gases released through sublimation are whatever ices were frozen into the nucleus. Water ice sublimates and releases water vapor. Carbon dioxide ice releases carbon dioxide gas. More complex molecules release more complex gases. By analyzing the composition of the coma, by measuring what wavelengths of light are being absorbed or emitted by the gases present, scientists can determine what the nucleus contains without ever touching it or digging into it. The coma is a natural sample extracted by solar heating. The brightness of the coma tells you about activity level. A bright, extensive coma suggests vigorous outgassing, lots of material being released, an active comet that's responding strongly to solar heating. A faint, compact coma suggests either less active outgassing, or a nucleus that doesn't have much volatile material left to release, or perhaps a nucleus that hasn't been heated enough yet to really get going. The characteristics of the coma, its brightness, extent, composition, structure, all combine to paint a picture of what kind of comet you're dealing with. When Psyche turned its instruments toward this interstellar visitor, scientists were particularly interested in what the coma would reveal. This wasn't just any comet. This was an object from another star system, potentially made of different materials, potentially with a different history of heating and cooling cycles, potentially representing a different stage of cometary evolution than what we see in our local comets. The coma data would be crucial for understanding whether interstellar comets are fundamentally similar to our own, or whether they display distinct characteristics shaped by their extrasolar origins. What Psyche observed was a coma that scientists described as faint. That single word, faint, carries significant meaning in astronomical terms. It means the coma wasn't as bright, wasn't as extensive, wasn't as visually prominent as some models suggested it might be at this stage of the comet's passage through the inner solar system. And faintness, in this context, tells you something important about what's happening on the nucleus. A faint coma could mean several things, and this is where scientific interpretation becomes a careful exercise in weighing evidence and considering alternatives. It could mean the nucleus has a low abundance of volatile ices, that much of its volatile material has already been depleted over countless passages near other stars or through regions of space where it experienced heating. It could mean the composition is different from typical comets in our solar system, perhaps richer in non-volatile material or ices that sublimate at different temperatures. It could mean the outgassing is concentrated in specific active areas on the nucleus, rather than happening uniformly across the surface, which would produce a less extensive coma. Or it could mean something about the grain size of dust particles being released. A coma's brightness depends not just on how much material is present, but on how that material scatters sunlight. Smaller dust particles scatter light more efficiently than larger particles. If this interstellar comet is releasing relatively larger dust grains, the coma might appear fainter even if the total mass of ejected material is substantial. The characteristics Psyche observed could reflect that grain size distribution, suggesting something about the physical properties of the dust embedded in the nucleus. What made Psyche's observations particularly valuable here was the multispectral nature of the data. The spacecraft didn't just measure overall brightness, it captured reflected sunlight across multiple wavelengths, from visible light into near-infrared. That wavelength information allows scientists to analyze not just how bright the coma is, but how that brightness varies with wavelength, and those variations tell you about composition and physical properties of the material present. The data showed wavelength characteristics consistent with a coma containing typical cometary dust, but with specific properties that suggested this interstellar visitor wasn't a perfect match for the average comet from our own Oort cloud. There were subtleties in the spectral signature, details in how different wavelengths were being reflected or absorbed that indicated compositional or structural differences worth noting. This is where the word unexpected becomes entirely appropriate. Scientists had models for what interstellar comets might look like. Those models were based on our understanding of comet formation in general, adapted to account for the different environments and histories that objects from other star systems might experience. But models are always approximations, always best guesses based on incomplete information. When actual observations come in, when you get real data from a real object, nature often surprises you with details the models didn't predict. The faint coma, with its specific spectral characteristics, represented one of those surprises. Not a dramatic overturning of expectations, but a refinement, a complication, a detail that said, this object is more nuanced than your simplified model suggested. And those details matter, because they're teaching us that interstellar comets, while broadly similar to our local comets in fundamental ways, display individual characteristics that reflect their unique origins and histories. Think about what this coma data represents in broader context. Here's an object that formed around another star, in a planetary system potentially very different from ours. It got ejected from that system through some gravitational interaction, possibly a close encounter with a planet, possibly the dynamics of planetary formation itself casting material outward. It has been travelling through interstellar space for an unknown amount of time, possibly millions of years, experiencing conditions far different from objects that remain bound to star systems. During that journey, it might have been bombarded by cosmic rays, exposed to interstellar radiation, subjected to micrometeorite impacts. All of those experiences could affect its surface composition, its ice content, its dust properties. Then it entered our solar system, passed close enough to the Sun to start outgassing, and revealed through its coma something about all that history, all those experiences all that time. Psyche's observations captured a snapshot of that revelation. The faint coma, the specific wavelength characteristics, the evidence of active outgassing but not vigorous outgassing, the suggestion of compositional or structural properties that differ subtly from typical comets, all of that is written in the data like a message from another stellar neighbourhood. Scientists will be analysing this data for years, comparing it with observations from other instruments, integrating it into models of cometary composition and evolution, using it to refine our understanding of how star systems form and evolve and exchange material with the broader galaxy. Because that's ultimately what interstellar objects represent. Evidence that star systems aren't isolated islands. They interact, they exchange material, objects get ejected from one system and potentially captured by another or pass through as temporary visitors. We're learning that the galaxy has a population of these wanderers, these interstellar drifters that carry information about their birth systems with them. Every observation we make of these visitors adds to our understanding of that population. Every detail we learn about composition, structure, behaviour contributes to building a picture of what's normal and what's unusual for objects originating in different stellar environments. The faint coma observed by Psyche is one piece of that larger puzzle, one data point in a growing catalogue of interstellar object characteristics. And here's what makes this particularly exciting. We're living through the era when humanity is first developing the capability to seriously study interstellar objects. A generation ago, we had never confirmed a single one. Today, we have detection networks sophisticated enough to spot them when they enter our solar system, and we have the instruments and expertise to study them before they leave. Every interstellar visitor we observe is adding to a database that didn't exist a decade ago. Psyche's 8-hour tracking session contributed to that database. The coma observations, the spectral data, the measurements of reflected sunlight across multiple wavelengths, all of it now sits in archives where future researchers will access it, combine it with other observations, use it to test theories about where this comet came from and what it can teach us about planetary system evolution across the galaxy. The faintness of the coma, which might sound like a disappointment to casual observers, is actually scientifically rich. It tells us this comet's activity level. It suggests something about its composition and structure. It provides constraints for models trying to explain the object's history. It raises questions about whether this represents typical behavior for interstellar comets, or whether we're seeing something unusual. All of those aspects are exactly what scientists want from observations, not just confirmation of expectations, but surprises that challenge us to think more carefully and deeply about what we're observing. And there's one more layer to this story, one more aspect of Psyche's contribution that deserves attention. The spacecraft's ability to capture this data at all, from millions of miles away, using instruments designed for a completely different target, speaks to something important about the flexibility and sophistication of modern space missions. We've reached a point where spacecraft can be multi-purpose, where instruments designed for one task can contribute to entirely different science when opportunities arise, where mission teams have the expertise and operational flexibility to seize those opportunities even when they weren't part of the original plan. That flexibility is what made Psyche's 8th-hour tracking session possible in the first place, and it's what will make future opportunistic observations possible as spacecraft travel through the solar system toward their primary destinations. Every spacecraft in flight is a potential observatory for unexpected targets. Every camera, every spectrometer, every instrument carries the possibility of contributing to science beyond its primary mission if the right opportunity presents itself, and if the mission team is creative and flexible enough to take advantage of it. Psyche proved that flexibility. It demonstrated that value, and it added to our knowledge of an interstellar visitor in ways that justify the 8 hours spent watching, waiting, and collecting data from a comet that came from somewhere beyond and is now heading back to that beyond, carrying with it the story of a brief encounter with humanity's instruments. But Psyche's contribution only matters in context, only gains full significance when you understand why this spacecraft could see things others might have missed, and how its unique position and capabilities complemented the broader observation campaign that multiple space agencies coordinated to study this visitor. That's the next layer of this story, the explanation of why Psyche's specific observations added value beyond what other instruments were capturing. There's a question that needs answering before this story can truly make sense, and it's the question you might have been asking yourself since the beginning. If NASA had multiple telescopes and spacecraft observing this interstellar comet, if Hubble was watching it, if ground-based observatories were tracking it, if other missions contributed data, then what exactly did Psyche add to the picture? Why did those 8 hours of observation from a spacecraft millions of miles away, a spacecraft designed for studying asteroids rather than comets, provide data that others couldn't capture? What made Psyche's contribution unique? The answer lies in understanding that space observation isn't just about having cameras and pointing them at things. It's about wavelengths, distances, angles, timing, and instrument sensitivity. Different observers see different things even when they're all looking at the same object, because each observer brings different capabilities and operates from different conditions. And sometimes, what one observer sees fills in gaps that others can't reach. Start with Psyche's multispectral imager. This instrument was designed specifically to analyze reflected sunlight across a range of wavelengths from visible light into near-infrared. That range was chosen because different materials reflect and absorb different wavelengths in characteristic ways, and by measuring how an object's brightness varies across wavelengths, you can determine what that object is made of. For a metal asteroid, which is what Psyche is designed to study, that capability lets you map composition across the surface, identifying regions that might be more metallic versus regions that might have more silicate material mixed in. But that same capability, when pointed at a comet, reveals information about the composition of the coma. Different gases absorb specific wavelengths. Different dust properties scatter wavelengths differently. By capturing reflected sunlight across Psyche's particular wavelength range, the spacecraft could analyze both what gases were present in the coma and what physical properties the dust particles had. Now, other observatories were doing similar analysis, but with different wavelength ranges and different sensitivities. Hubble, for instance, has instruments that can observe ultraviolet wavelengths that Psyche can't see, and UV observations are particularly valuable for detecting certain gases and studying gas emission rather than just reflected sunlight. Ground-based infrared telescopes can observe longer wavelengths than Psyche captures, wavelengths that reveal information about temperature and thermal emission. Each instrument adds a piece to the complete spectral picture of the comet, and Psyche's contribution was filling in the visible to near-infrared range with space-based observations that didn't have to deal with Earth's atmosphere. That last point is crucial. When you observe from Earth's surface, you're looking through miles of atmosphere, and that atmosphere absorbs and scatters certain wavelengths, creates noise in your data, and limits what you can see. Space-based observations eliminate that problem entirely. Psyche, operating in the vacuum of space, could capture wavelengths and detect subtle features that ground-based telescopes might struggle with, even large professional observatories with sophisticated instruments. But Psyche had another advantage that's less obvious and more interesting: its position in space during the observation window. The spacecraft was millions of miles away from Earth, at a different location in the solar system, observing the comet from an angle that no Earth-based telescope could achieve. That different viewing angle meant Psyche saw the comet with different lighting conditions, different geometry, and potentially different features emphasized than what observers from Earth's vicinity would see. Think about how lighting changes what you can observe. When you look at the moon from Earth, you see different features depending on the phase, on where the sun is relative to the moon and your position. Full moon washes out subtle features but shows overall brightness distribution. Crescent moon creates dramatic shadows that reveal topography. The same principle applies to comets. Observing from different angles with different lighting can reveal features that are hidden or less prominent from other viewpoints. Psyche's position during the 8-hour tracking session provided one such alternate viewpoint. The angle between the sun, the comet, and the spacecraft was different from the angle that Earth-based observers had, which meant the way sunlight scattered off the coma's dust particles was different, which meant Psyche could measure aspects of particle size distribution and optical properties that might not be as apparent from other angles. Distance also played a role, though not in the way you might initially think. Yes, being millions of miles away meant the comet appeared smaller to Psyche's cameras than it would to closer observers, but it also meant Psyche was observing the comet in context with surrounding space in ways that very close observations can't achieve. Psyche could see the overall structure of the coma, the way it extended outward from the nucleus, the way brightness fell off with distance from the center, without being so close that the view became dominated by small-scale details. That broader perspective complemented the detailed close-up views that other instruments were capturing. There's also the matter of timing. Psyche's 8th-hour tracking window happened at a specific point in the comet's passage through the solar system. By that point, other observers had been watching for some time and would continue watching afterward. Psyche's observations provided data from that particular moment, adding time series information that helped scientists understand how the comet's behavior was evolving as it moved along its trajectory. Comets change as they approach and recede from the sun. Activity levels vary. Coma characteristics evolve. Having observations from multiple times allows you to construct that evolutionary picture, and Psyche contributed observations from its specific time window that filled in part of that timeline. The combination of all these factors, wavelength coverage, space-based clarity, unique viewing angle, appropriate distance, specific timing, meant Psyche could contribute data that genuinely added value to the overall observation campaign. This wasn't redundant information. This wasn't just another dataset confirming what everyone already knew. This was complementary data that filled specific gaps, that provided measurements from conditions other observers couldn't replicate, that added pieces to the puzzle nobody else could provide. And there's something almost poetic about the fact that this contribution came from a spacecraft that was never designed to study comets at all. Psyche is an asteroid mission. Its instruments were chosen and calibrated for studying a metal-rich asteroid. But the fundamental physics of how those instruments work, capturing reflected sunlight, analyzing wavelengths, measuring brightness, applies to any object that reflects light. With appropriate planning and skilled operation, those instruments could be turned toward a completely different target and still return scientifically valuable data. This adaptability is one of the quiet triumphs of modern space exploration. We design missions for specific targets, but we build spacecraft with capabilities that extend beyond those narrow specifications, and we train mission teams to think creatively about how their instruments might contribute to unexpected opportunities. When an interstellar comet appears, when the call goes out for all available observers to contribute data, spacecraft like Psyche can answer that call even though comets are nowhere in their mission documentation. The engineers who designed Psyche's multispectral imager probably never imagined it would be observing an interstellar comet, but they built an instrument with fundamental capabilities that could be applied to various targets. The mission planners probably never had track interstellar objects in their original operational timeline, but they maintained the flexibility to adjust schedules when opportunities arose. The scientists analyzing Psyche's data were focused on preparing for asteroid observations, but they had the expertise to interpret cometary observations as well. All of these human elements, engineering foresight, operational flexibility, scientific breadth, combined to make Psyche's 8-hour tracking session possible and productive. The technology mattered. The spacecraft's position mattered. But ultimately, it was human decisions and human expertise that transformed those hours into meaningful contributions to our understanding of a visitor from beyond our solar system. And that brings us to the bigger picture, the broader context in which Psyche's observations sit. Because this wasn't just one spacecraft doing its own thing, this was one participant in a coordinated multi-asset observation campaign that NASA orchestrated to maximize our scientific return from this interstellar visitor's passage through our solar system. Understanding that coordination, appreciating the scale of the effort that went into studying this comet from every available vantage point, puts Psyche's 8 hours into proper perspective and shows you how modern astronomy tackles rare opportunities with everything at its disposal. When an interstellar object enters our solar system, it doesn't just capture the attention of a few astronomers, it activates a response from the entire space science community. And at the center of that response is a coordinated effort by NASA to bring every available resource to bear on studying the visitor before it leaves. Psyche's 8-hour tracking session was one component of a much larger observation campaign, a campaign that included multiple spacecraft, multiple space telescopes, and ground-based observatories all working toward the same goal, understanding this messenger from another star system before it slipped back into the interstellar void. Think about what it takes to coordinate something like that. You have spacecraft in different locations, each with their own mission schedules, their own operational constraints, their own teams of engineers and scientists. You have telescopes with observation time allocated months in advance to approved research programs. You have ground-based observatories that depend on weather and can only observe when the target is visible from their location. Getting all of these assets to focus on a single target, to coordinate their observations so they complement each other rather than duplicate effort, to share data in real time so everyone benefits from what everyone else is seeing. That requires institutional commitment and coordination at the highest levels. NASA made that commitment for this interstellar visitor. The decision was made that this object was significant enough, scientifically valuable enough, rare enough that it warranted mobilizing assets across the agency. And so the call went out. Hubble would observe, James Webb Space Telescope would contribute its unique infrared capabilities, Mars orbiters would attempt observations from their vantage points. And spacecraft like Psyche, even though they were en route to other destinations, would participate if their positions and capabilities allowed useful contributions. The result was an unprecedented multi-mission observation campaign focused on a single interstellar object. Different wavelengths covered by different instruments, different viewing angles from different locations in space, different times sampled as the comet moved along its trajectory. All of that data flowing back to Earth, being analysed, being shared among researchers, being integrated into comprehensive models of what this visitor was and where it came from. Hubble's contributions focused on detailed imaging and ultraviolet spectroscopy, revealing the comet's overall structure and detecting specific gases through their ultraviolet emission lines. James Webb's infrared capabilities allowed observation of thermal emission and gases that are best detected in infrared wavelengths. Ground-based observatories around the world contributed optical and infrared observations whenever the comet was visible from their locations, building up time series data showing how the comet's brightness and activity evolved. And spacecraft like Psyche added their unique perspectives from locations in deep space. Each contribution mattered, each dataset added information, and the synthesis of all these observations created a picture of the interstellar comet that no single observer could have achieved alone. This is modern astronomy at its best, collaborative, comprehensive, making maximum use of humanity's collective observational capabilities to study something that won't come around again. But there's another layer to this story that's worth understanding, and it has to do with planetary defense. NASA's commitment to tracking interstellar objects isn't purely about scientific curiosity, though that's certainly a major driver. It's also about maintaining and exercising the infrastructure that protects Earth from potential impact threats. When you have the capability to detect, track, and characterize objects entering our solar system, you're building skills and systems that apply equally well to potentially hazardous asteroids from our own neighborhood as to interstellar visitors. This interstellar comet posed no threat to Earth. NASA confirmed that explicitly and repeatedly. The trajectory calculations, including the refinements made possible by multi-mission observations like Psyche's, showed conclusively that the object would pass through our solar system at safe distances from all planets. But the act of tracking it, of coordinating observations, of refining trajectory predictions, of analysing composition. All of that is practice for the systems and teams that would need to respond if a more concerning object appeared. Planetary defence isn't just about having telescopes and spacecraft. It's about having practiced, coordinated teams who know how to work together quickly and effectively when time is limited. It's about having operational procedures in place for mobilising assets. It's about having the infrastructure to share data rapidly and analyse it collectively. Every interstellar object that passes through gives NASA and its partners an opportunity to exercise those systems, to identify what works well and what could be improved, to keep teams sharp and procedures current. So when Psyche participated in tracking this interstellar comet, the spacecraft wasn't just contributing to abstract scientific knowledge. It was participating in an exercise of humanity's collective capability to observe, track, and understand objects that move through our cosmic neighbourhood. That capability has both immediate scientific value and long-term practical importance for planetary protection. The coordination demonstrated during this observation campaign shows how far we've come in our ability to respond to astronomical opportunities and potential threats. A few decades ago, we would have been lucky to get decent images of an interstellar visitor from a single ground-based telescope. Today, we can coordinate multiple space-based observatories, multiple spacecraft, and dozens of ground-based facilities to create a comprehensive observational dataset that captures the object from every available angle and wavelength. That's progress, that's capability, and that's reassuring when you think about what else might come through our solar system in the future. NASA's commitment to this observation campaign also reflects a broader understanding that interstellar objects represent extraordinary scientific opportunities. We can study objects from our own solar system anytime we want. They're here. They're not going anywhere. We can plan missions years in advance, take our time designing instruments, schedule observations at our convenience. But interstellar visitors don't wait for us. They pass through on their own schedules, and if we don't study them during their brief passage, we lose the opportunity forever. That sense of urgency drives decisions like the one to have Psyche track the comet for 8 hours. This was an opportunity that wouldn't repeat. The object would never come back. Whatever data we could gather during its passage through our solar system was all we would ever get. And so NASA made the call to mobilize everything available, to capture as much information as possible while the opportunity existed. The collaborative nature of the campaign also reflects something important about how science works at this level. No single institution, no single country, no single space agency has a monopoly on capability or expertise. NASA coordinated much of the effort, but astronomers around the world contributed. International observatories participated. Data was shared freely among researchers. This was humanity collectively studying a visitor from beyond, and that collaboration maximized what we could learn. The data gathered from all these sources is now being analyzed, published, and integrated into our growing understanding of interstellar objects. Papers are being written, models are being refined. Future observations of other interstellar visitors will be informed by what we learned from this one. And Psyche's 8th-hour contribution is now part of that permanent scientific record, cited in research, included in datasets, used to constrain models of cometary composition and behavior. That's the bigger picture. That's the context in which Psyche's tracking session matters. It wasn't an isolated observation. It was one coordinated element of a comprehensive campaign that demonstrated both our capability and our commitment to studying these rare visitors. And as Psyche continues its journey toward its primary target, as the spacecraft moves farther from Earth and closer to the metal asteroid it was designed to explore, those 8 hours spent watching an interstellar comet will stand as evidence of what modern space missions can accomplish when opportunity and capability align. The observation campaign for this interstellar visitor is now complete. The data is collected. The object has continued on its path and will soon be too far and too faint for even our most powerful telescopes to observe. But the scientific work continues, and Psyche's contribution remains part of the foundation on which that work builds. And as for Psyche itself, this spacecraft has its own journey to complete, its own destination awaiting, and its own discoveries still ahead. Those 8 hours tracking an interstellar comet were a detour, a scientifically valuable pause in a much longer journey that Psyche is still undertaking. The spacecraft's primary mission, the reason it was built and launched, remains ahead of it, and understanding where Psyche is now, where it's going, and what it will do when it arrives puts those 8 hours of comet observation into perspective as one chapter in a multi-year story of exploration that won't reach its climax for several more years. Right now, as you're reading this, Psyche is millions of miles from Earth, travelling through the inner solar system on a trajectory carefully calculated to eventually deliver it to the asteroid belt. The spacecraft is healthy. Its systems are functioning as designed. Its instruments remain ready for the science they were built to perform. But Psyche still has years of travel ahead before it reaches its destination, and during that journey, the spacecraft will pass several important milestones. The next major event in Psyche's mission timeline is a gravity assist flyby of Mars scheduled for May of next year. This maneuver is crucial for the mission's success. When Psyche passes close to Mars, the planet's gravity will bend the spacecraft's trajectory and increase its velocity, essentially giving Psyche a free speed boost that would have required carrying much more fuel if achieved through rocket propulsion. This kind of gravity assist is a standard technique in interplanetary navigation, used by countless missions to reduce fuel requirements and enable journeys that would otherwise be impossible or prohibitively expensive. The Mars flyby will be brief but significant. Psyche won't be studying Mars. That's not what the spacecraft is designed for, and the flyby will happen quickly, with the spacecraft using Mars purely as a gravitational slingshot to alter its course. But mission teams will monitor the flyby carefully, tracking the spacecraft's trajectory change, confirming that the gravity assist delivered the expected velocity change, and ensuring all systems remain healthy as Psyche continues toward the asteroid belt. After Mars, Psyche will continue outward, climbing away from the Sun's stronger gravitational influence, moving toward the region between Mars and Jupiter, where millions of asteroids orbit in the main belt. And somewhere in that belt, orbiting the Sun at a carefully predictable location, is the spacecraft's ultimate target, a massive metallic asteroid that represents one of the most intriguing objects in our solar system. That destination won't be reached until July of the late 20s, still several years away. When Psyche finally arrives, it will begin a detailed orbital study of the metal-rich asteroid, using all its instruments to map the surface, determine composition, measure magnetic fields, and characterize this bizarre world that might be the exposed core of an early protoplanet. The mission is designed to orbit the asteroid for an extended period, gathering data that will help scientists understand planetary formation, planetary differentiation, and the processes that create metallic planetary cores. The science Psyche will conduct at its primary target is genuinely exciting. We've never studied a metallic world up close before. We've visited rocky asteroids and icy bodies, but a metal-rich asteroid potentially representing a planetary core? That's entirely new territory. The data Psyche will gather could revolutionize our understanding of how terrestrial planets like Earth formed, how their interiors are structured, and how magnetic fields are generated in planetary cores. But all of that is still years in the future. For now, Psyche is in what's called the cruise phase, the long period of interplanetary travel between launch and arrival. During cruise phase, spacecraft teams maintain the vehicle, monitor systems, occasionally test instruments, and plan for upcoming mission phases. It's the quiet middle of the journey, less dramatic than launch or arrival, but absolutely essential for mission success. And during that quiet middle, opportunities like the Interstellar Comet tracking session occasionally arise. These bonus science activities don't interfere with the primary mission. They're carefully planned to fit within the spacecraft's operational constraints, but they do add value beyond what the mission was originally designed to deliver. Psyche was built to study one specific asteroid, but during its journey to that asteroid, it contributed to our understanding of an interstellar visitor. That kind of opportunistic science represents excellent return on the investment in spacecraft capability. As Psyche continues toward its destination over the coming years, the spacecraft might have other opportunities to contribute to science beyond its primary mission. If another interstellar object appears at the right time and place, if an asteroid in Psyche's path is worth imaging during the journey, if some other astronomical event occurs that the spacecraft could observe from its unique location, mission teams might make similar decisions to dedicate some observation time to those targets. Flexibility in mission operations creates opportunities for bonus science, and Psyche has demonstrated that flexibility. But make no mistake, the primary mission remains the focus. Everything Psyche does during cruise phase, every system test, every instrument calibration, every operational procedure is ultimately in service of preparing for arrival at the metal-rich asteroid. The 8 hours spent tracking the interstellar comet were valuable, but they were a side activity, a brief diversion from the main purpose. The spacecraft's trajectory wasn't altered. Its primary timeline wasn't compromised. The observation was carefully planned to avoid any impact on the mission's ability to reach its destination and perform its designed science. That balance between primary mission focus and opportunistic science is something NASA manages carefully across all its missions. Spacecraft are expensive, mission time is limited, you can't allow secondary activities to jeopardize primary objectives, but when opportunities arise that can be accommodated without risk, when bonus science can be achieved within existing operational margins, taking advantage of those opportunities is smart use of assets and taxpayer investment. Psyche's 8th-hour Comet tracking session exemplified that balance perfectly. The observation contributed valuable data to an important astronomical event. It demonstrated the spacecraft's capabilities and the team's operational flexibility. It generated public interest and helped communicate the value of space exploration. And it did all of that without compromising anything about Psyche's ability to complete its primary mission at the metal-rich asteroid years from now. As the spacecraft continues its journey, as the months turn into years and Psyche moves steadily toward its destination, those 8 hours tracking an interstellar visitor will remain part of the mission's history. They'll be mentioned in mission summaries and science papers. They'll be used as examples of opportunistic science and operational flexibility. And the data captured during those hours will continue contributing to our understanding of interstellar objects long after Psyche has arrived at its asteroid and completed its primary science mission. The journey continues. The spacecraft travels onward through space, carrying instruments that will eventually reveal secrets about planetary formation locked inside a metal-rich asteroid. And along the way, for 8 hours in early September, those same instruments briefly turned toward a comet from another star system and captured something unexpected. Something that added to human knowledge in ways that justify every decision that made those observations possible. Psyche will reach Mars for its gravity assist. It will continue outward to the asteroid belt. It will eventually arrive at its destination and begin the science it was designed to perform. And throughout all of that, the mission will stand as evidence of what we can achieve when we build sophisticated spacecraft, train expert teams, and maintain the flexibility to seize unexpected opportunities when they arise. Step back from the technical details for a moment and consider what this story actually represents. An interstellar comet, an object that formed in another star system countless ages ago, travelled through the void between stars for who knows how long, entered our solar system, and revealed something about itself to humanity through observations captured by a spacecraft that wasn't even designed to study comets. That chain of events, that intersection of cosmic wandering and human capability, tells us something profound about where we are as a species and what we're learning to do. We're learning to reach beyond our immediate neighbourhood and touch, at least intellectually, objects from elsewhere in the galaxy. That's extraordinary when you think about it. For all of human history until very recently, we could only study objects bound to our own solar system. Planets, moons, asteroids, comets, all of them part of our local family, all of them shaped by the same stellar neighbourhood, all of them limited to teaching us about this one system orbiting this one star. But now we're detecting and studying objects from beyond. We're capturing light that reflected off worlds and visitors from other stellar environments. We're analysing that light to determine composition, structure, behaviour. We're learning what's the same and what's different between our corner of the galaxy and others. And every data point we gather, every observation we make, every interstellar visitor we study adds to a body of knowledge that's teaching us how planetary systems in general work, not just ours specifically. That knowledge has practical implications beyond satisfying curiosity. Understanding how planetary systems form, how they evolve, how they exchange material with their surroundings informs our search for planets around other stars and our assessment of where life might exist beyond Earth. If we know that interstellar objects regularly travel between star systems, we understand that material can be transported between stellar neighbourhoods, potentially spreading the chemical building blocks of life across greater volumes of space than we might have thought. If we know how comets from different environments differ in composition and behaviour, we understand the range of conditions under which these objects form and what that diversity means for planetary system architecture. Psyche's 8th-hour observation of an interstellar comet contributes to that broader understanding in its own small but meaningful way. The data about the faint coma, about the spectral characteristics, about the trajectory and behaviour of this visitor, all of that feeds into research programs trying to answer fundamental questions about how the galaxy works at the larger scales and how individual objects like comets fit into that larger picture. And there's something hopeful in recognising that we're living through the era when humanity first develops these capabilities. Our grandparents didn't have confirmed interstellar objects to study. They theorised such objects must exist but never saw one. Our children will grow up in a world where studying interstellar visitors is routine, where we have catalogues and statistics and comparative data about objects from various stellar neighbourhoods. We're the transition generation, the ones who remember when this wasn't possible, and who now get to witness it becoming normal. That transition is happening because of investments in space exploration that span decades. The spacecraft, the telescopes, the mission teams, the scientific expertise, none of it appeared overnight. It's the result of sustained commitment to understanding our place in the cosmos, commitment that justifies itself through discoveries like the ones Psyche contributed to during those 8 hours in September. Think about the coordination that made those observations possible. Engineers who designed and built a spacecraft years ago, planning for a mission to a metal asteroid. Launch teams who sent that spacecraft on its way. Mission operators who maintain it day by day as it travels through space. Scientists who prepare for the eventual arrival at the primary target, but who also remain alert for opportunities like tracking an interstellar comet. Astronomers who detected the comet in the first place, and who coordinate observation campaigns across multiple facilities. Researchers who analyze data and extract meaning from measurements of reflected light. The entire chain of human expertise and collaboration that transforms photons bouncing off an ancient object into understanding we can communicate and build upon. That collaboration, that long chain from engineering to analysis to understanding, represents something important about how we explore the universe today. It's not lone genius having sudden insights. It's teams working together across institutions and nations, building on each other's work, contributing their specialized expertise to collective goals. Space exploration in the modern era is fundamentally collaborative, and that collaboration makes possible achievements no individual or single institution could accomplish alone. The 8 hours Psyche spent tracking an interstellar comet demonstrated that collaborative spirit perfectly. One spacecraft among many observers, one dataset among many contributions, one piece of a larger puzzle that required everyone's participation to complete. And the result is knowledge we didn't have before, understanding we've added to humanity's permanent record, information that future generations will build on as they continue exploring and learning. As this interstellar visitor continues its journey outward, heading back into the space between stars, it carries no knowledge of having been observed. It's just an ancient chunk of ice and rock following gravitational physics wherever it leads. But for the brief time it passed through our solar system, it connected with humanity in a meaningful way. We saw it, we studied it, we learned from it, and now as it leaves we're different than we were before it arrived, because we know things we didn't know before, because our understanding of the universe has expanded by the increment that this visitor enabled. That's what exploration does. It changes us. Not always in dramatic ways, not always in ways that immediately affect daily life, but in cumulative increments that build over time into transformation. Every space mission, every observation, every data point adds to the collective knowledge that shapes how we understand our place in the cosmos. And occasionally, when opportunities align perfectly, when a spacecraft designed for one purpose can contribute to studying something entirely different, we get moments like Psyche's 8-hour tracking session that exemplify the best of what exploration can achieve. The data captured during those hours will be referenced in scientific papers for years to come. Researchers studying interstellar objects will include it in their analyses. Future observation campaigns will learn from the coordination and techniques demonstrated here, and somewhere in archives, the images and spectral measurements will wait for some researcher in the future who might extract new insights from them with tools and understanding we don't have yet. That's the nature of good data. It has value beyond its immediate analysis. It becomes part of the permanent record that future scientists can revisit with fresh perspectives and new questions. Psyche's contribution to studying this interstellar visitor isn't finished just because the observation is over. It will keep contributing as long as people care about understanding objects from beyond our solar system, and we will keep caring because humans are curious by nature, and interstellar visitors tap into something deep in that curiosity. They come from elsewhere. They carry information about places we can't visit. They connect us to the broader galaxy in tangible ways. Every time one appears, we drop what we're doing astronomically and pay attention, because the opportunity is rare and the potential for learning is enormous. Psyche's 8 hours tracking a comet from another star system represent one chapter in that ongoing story of attention and learning. The spacecraft did its part. It captured data that surprised scientists and contributed to our understanding, and now it continues toward its own destination, toward discoveries that are still years away, but that will ultimately justify everything about this mission. But for 8 hours in September, Psyche was part of something bigger than its primary mission. It was part of humanity's response to a visitor from beyond, part of a coordinated campaign to extract maximum understanding from a fleeting opportunity. And what it found during those hours, the unexpected characteristics of a faint coma revealing details about an ancient traveller from another stellar neighbourhood, adds to the foundation of knowledge we're building about the galaxy we inhabit. If this 8th-hour window into an interstellar visitor left you with more questions, you're exactly where you should be. That's what discovery feels like. It doesn't close doors, it opens them. It reveals how much we still don't know and invites us to keep looking, keep learning, keep building the capabilities and expertise needed to find answers. Drop a comment with what surprised you most about Psyche's observations. Hit subscribe to follow updates as the spacecraft continues toward its primary destination, and as other interstellar visitors inevitably appear in our solar system to be studied with everything we have. And stay curious, because the universe keeps sending messengers, and we're getting better at listening to what they have to tell us. The 8 hours are over. The comet has moved on, but the knowledge remains and the journey continues. Both for Psyche and for humanity's ongoing exploration of the cosmos, we're learning to understand one observation, one discovery, one unexpected finding at a time. Thanks for tracking this story with me.